Hello and welcome back on Root Access Berlin. We are here again at the Factory Studio for the second episode on SQL versus NoSQL. I have with me Nacho Coloma from the company Koliseo. So first of all, tell us again what Koliseo is.
Koliseo is a ticketing platform that is focused on making the ticketing experience as simple and as fast as possible.
Now we would like to hear your expert advice on how to work around some of the limitations of NoSQL databases. What are the tips, tricks, and what is the secret sauce that you use at Koliseo?
Yeah, in the last episode we were talking about the difference between SQL and NoSQL databases. Today we're going to focus on tricks. How do you work around the limitations?
In the process of building Koliseo, you acquired a lot of expertise on App Engine and the data store, and you are publishing this library called SimpleDS,
Yep.
which makes it easier to work with the data store because it provides a mapping between Java classes and data store entities.
Yeah, that's right. It's available at GitHub, and also there's a lot of introductory materials to SimpleDS. So I invite everyone to try it out.
And so the alternatives to SimpleDS, so JPA and JDO, that's what the documentation says.
Yep. And
But
Objectify is what a lot of people are using also these days.
But I think we agree that people are better off using either Objectify or SimpleDS.
Yeah, you should try to shy away from JDO or JPA because they are too generalistic solutions. They are focused on SQL databases, and the NoSQL problems are extremely different.
So we came up last time with this 5-point list for helping people decide between SQL and NoSQL. We've seen that on the scalability front, NoSQL is unbeatable. That also a lot of people feel that a NoSQL database can represent their data in a more natural way, although that is a philosophical discussion. But in the SQL world, you have the power of the SQL language. How do you work with queries in NoSQL?
If you are trying to execute a query, you need to have an index for every field that is involved, for every property that is involved in that query.
Let's take the example of a ticket that we store as an entity in a NoSQL data store. And, well, first of all, I want to find all of the tickets that belong to a given event. So my ticket has an event key.
Yep.
But I need to do something extra to be able to query by that key.
First of all, if you are only asking for tickets with a certain event key, in the App Engine data store, all entities, all properties in an entity are by default indexed. You have a single index, you have an index for a single property that is the event key. If you are only going to ask, give me all the tickets with this event key, you can have that out of the box.
But still, it costs me storage.
Yep. Every index that is stored with your entities takes space and takes performance as well. So at some point, you will most certainly have more space dedicated to indexes than to the information itself.
And so what do I need to do now if I want to query by two properties? Like here, for instance, I want to get all the tickets relating to this event and then sort them by their creation date, for instance.
Yeah, not only when you are querying by a property, also when you are sorting, you need an index for that. When you are doing it with more than one property at the same time, you need to create a composite index.
And so this multiple index will also cost me, of course, storage space.
Yep.
So what are the storage space saving tricks that you can recommend? For instance, you told me that for some requests, you might want to filter in memory instead of asking the data store to do the filtering for you.
Yeah, there are several possibilities here. First of all, if you want you can disable automatic indexing for single properties. If you know for sure that a property is never going to be used in a query, then you can just store it as unindexed and it will not take that extra space. Another case that we are finding a lot, when you have a query and you are reasonably sure that the criteria for selecting is always going to be, is 99% of the time going to be a match for your query, then you can do that in memory. For example, in this case, we are executing a query of all the users with a certain role. Now we're only interested in users that are enabled. You can add that and use a composite index, but that's a waste because 99% of your users are enabled. This is, in this case, you can assume that it's not frequent to find disabled users. In that case, what we're doing here, we're using Guava predicates to filter. This is a filtering that is done in memory. This query will return you a paginated query. And before returning you the list of data for this page, it's going to filter in memory according to the predicate that you have passed. A predicate is a function that is inside Guava. Guava is one library that is from Google, actually, an open source library that allows you to manipulate collections of data. So in this case, what we are doing is to filter and return only users that are not disabled.
Another problem you told me about is that in the NoSQL world, you don't have joins.
Yeah, and that's a problem actually, because if you want to show data from two different entities at the same time, you cannot do that as you would with SQL. It's a no-brainer. You have two entities, you want to put one along the other, you just make a join and everything is working.
So for instance here, you want to show a list of users and next to each user you want to display his last post.
Yep. And
so that would be a join in the SQL world.
That's right. You have two different entities and you want to put one beside the other.
So the simple solution that I would implement would be something like this. I would run a query to return all of my articles, and then for each article I would run a separate query to return its author.
Yeah.
Why is that a bad idea?
This is the typical first approach to this problem. You have the list of articles and then you're going to ask for each user one over and over and over again. What happens is that each time you go to the data store, it's an expensive operation in terms of CPU, in terms of time. And you are making these calls sequentially, one after the other. So if, for example, you have 20 articles, you're going to request 20 times to the data store to get the users back. Instead of that, the approach that you should try to do is to process all the articles, get all the keys, and then require all the users in a single request.
So here we are assuming that our articles, inside of the article you have a user key that is stored. Mm-hmm. And so you get the articles, you get the collection of keys, and then the data store has a built-in functionality which is called batch queries, where you can provide this list of keys and it will return a list of users.
You can request, I want to get all these keys in a single operation and they will get back. You don't have to do anything special for that. That's a good thing of NoSQL storage, that you can ask for a set of keys and they will come back right away.
So let's look at the code here for executing this. So the red line here is what I understand. I call the data store, I give it a bunch of keys, and in return I get a map of users.
What we have here is we are retrieving the articles, then we are transforming, again, we're using Guava for this, we're transforming all the articles into their user keys. And
so here simply instead of doing an iteration, you use this, this trick that looks like functional programming that comes with Guava, where you can provide a mapping function that returns a user key from an article entity.
That's right. Entity to property function is something that comes with SimpleDS. SimpleDS has several tricks like this to make easy the functional programming part of working with NoSQL, because these are cases that go over and over again. When you're working, you're always faking joins, you're always filtering in memory because of the limitations in the platform. So SimpleDS is designed to help you with that, trying to make it easier.
So we went through the art, I would say the black art of querying the data store. Another limitation that is quite painful, frankly, is the lack of database schemas. Some people like very strict schemas, and some people like the freedom that a NoSQL database offers. But it also means that in a NoSQL database, you will have to maintain the integrity of your data structures basically by hand.
Yep. Say, for example, that you want to add new fields to an existing structure. That would be an alter table, right? You would just add a column and it's already there. And maybe you can also assign a default value and it's already initialized. You don't have to do anything special for that.
So that would be one operation in a SQL database.
That's right. That's right, but not in NoSQL. In NoSQL, you don't have any schema, meaning that every instance is independent. If you want to add a property and you want it to exist in all the existing instances in the data store, then you have to execute that by hand. You have to go one by one, adding the property, then storing the instance, going to the next one, etc., etc.
So let's stop a minute here. You told me before that I cannot do any full table scans because only indexed queries are going to work. But here I need to go through all of my entities of the whole data store to upgrade them to my new data model.
Yeah, you can do that using cursors. Cursors work in NoSQL more or less the same way they do in SQL databases. You have a big set of data to process. You can use cursors to postpone work, to say, okay, I stopped here and I want to restart this query again later. So you can work in chunks of work and keep postponing work. So let's say, for example, one common practice when you're working with NoSQL data stores is to denormalize your data. We were talking about how you had different collections of articles and users, and you wanted to transform your articles into users. But if your operation is, say, executing 80% of the time, because, for example, it's part of your homepage or whatever, it's happening over and over again. What you usually do in NoSQL databases is to denormalize data, to get into the article the fields that I need from the user for 80% of the cases.
So that's what we see here in this example. I added into my article entity those three red fields, username, user email, user avatar, that are duplicated from the user entity.
Yeah, and you will have to keep those by hand. If the user is modified, you will have to cascade these changes to all the articles by that user. But the thing is, how do you introduce this into an already working database, into your already working application? With a new upgrade, you need to modify your data to denormalize it, and it's going to apply to all the existing articles. So you have to modify all of them.
Let's see an example. I understand the code here. I understand the three red lines in the middle. That is where we are setting the username, the email, and the avatar on the article coming from the user. I also understand that we have a for loop around this. We are doing an iteration on all of our articles. And actually the first red line, that is a query that is returning all of my articles. But of course, this is going to be a lot of articles.
Yeah, and you have limitations that you should always be aware of in App Engine. In App Engine, all requests should be ending by 30 seconds. You can be executing in a backend, or you could be executing in a query, in a task queue. But in any of these cases, your query has an expiration time of 30 seconds. So if you're going to execute a long-running query, because you have to process a lot of results, you should be stopping after some time and retasking again, rescheduling your remaining work.
And so the problem here is that you need to know when your query is about to time out. So you're using a different library which has this query timeout function. But then once you stop processing your articles and you know that you have not finished, how are you resuming this operation?
In this case, what we're doing is to return a cursor. If you're returning a not null cursor, then I assume that you have not finished. So I reschedule to execute again, or I just call it right away again because I have enough time.
So you are putting that cursor into a task which you are putting onto the task queue again,
yeah,
and it will be executed at a later point in time.
That's it.
But you need all that to be finished before you upload the new version of your software that is using those new fields.
That's right. That's right. You should design this kind of task to be idempotent, in the sense that you can execute them over and over again and it will work. Or you can also work with MapReduce if you want. That's going to be faster on one side. On the other side, it's going to be a bit more complicated to configure. It's your choice.
The last point that I would like us to discuss is coherence. So you have a very good example of that using events and tickets. So first of all, tell us why you need a transaction to buy a ticket.
When you are buying a ticket, you need transactions in NoSQL data stores the same way you need them in SQL databases. You need to change two entities and they have to behave transactionally. Either the two of them are modified or not. An event has the number of available tickets. Let's say, for example, 100. When I am buying a ticket, I am creating a new entity, and you want that to behave transactionally. I want to reduce the number of available tickets, I want to create my ticket, and that has to happen, both of them or neither at all, nothing at all. So in that case, what you do is to create your transaction, make all your modifications, and commit or roll back the transaction.
But in order to do that, I need to have my event and my tickets in the same entity group, or at least I needed to until App Engine implemented cross-group transactions.
Yeah, that's right. It's more flexible, and now you can make cross-group transactions, XG transactions, that can put up to 5 different entity groups in the same transaction.
But you say this is not actually a good way of organizing things, because we have a write limit of something like 1 to 5 writes per second to the same entity group. Mm-hmm. It means that only a maximum of 5 people can be trying to buy the same ticket at the same time, and the quantities that you are handling in real events are way larger than that.
Yeah, that's right. So another option, more realistic to apply entity groups, because not all master detail relationships are suitable for entity groups, but we had a similar case for users. Now, what we're doing with this, the good thing is that a user is not that fast interacting with the system. So if you want to make a transaction between a user and his tickets, for example, if you want to keep a counter on the number of tickets that the user has purchased over time, you can do that transactionally, and you have the guarantee that the user is not going to be clicking that fast. So for that, a transaction is reasonable.
So that is actually a good rule of thumb, that it's a good idea to organize the elements relating to your users into entity groups, because one user is not likely to be buying so many tickets at the same time, but this still allows a lot of different users to be hammering the system at the same time in hundreds and thousands.
That's right. You usually don't have contention on the user level. You have it somewhere else, but a single user is not that fast interacting with the system.
And so here, for the relationship between a user and a ticket, you group those into an entity group. So you can do your transactions easily there. And if we come back to events and tickets, as you said, you do not put them in the same entity group because that would limit the number of tickets you can sell per second.
It's going to be more complicated than that because contention is not an easy problem in any case. It's not something that you can solve with transactions so easily. But these are more or less the typical two cases. You can choose to make an entity group and around your transactions, or you can choose to keep your entities separate. For example, if you don't have, because as I told you, parent, all your entities can have at most one parent. So maybe your transactions don't fit into that model, and then you have to use cross-group transactions. Those are your two options with App Engine.
Thank you, Nacho. Thank you for these tips and tricks on using the data store.
Thank you.
And we will see you in the next episode of Root Access Berlin. Thank you.